Hello, everyone. Welcome back. Welcome back to Calc 1000. Today, we are planning to go a bit further in the section 4.5, which is derivatives and the shape of the graph of a function. Last time we studied what are the implications of the first derivative on the function itself, which was about increasing, decreasing. And then out of that, we were able to create what's called the first derivative test. Today, we are going to go one derivative higher, the second derivative. First, we will try to understand. First, we are trying to understand how the second derivative makes us understand the graph of the function more. And then we will use that to cook up another test for relative max-min, which is called, obviously, the second derivative test. We will have a bunch of examples, bunch of ideas there. But before I start, is there any questions, any comments? OK, let's then start. Second derivative test. Remember yesterday, or Monday, we were talking about the increasing, decreasing functions, yes? What makes a function increasing or how we can understand when the function is increasing comes from the fact that the first derivative is positive. If the first derivative is negative on an interval, then the function is decreasing. Now let's focus on increasing function for a second. I can draw these two functions. This is a graph of an increasing function. This is also a graph of an increasing function. I want you to talk to your friend sitting next to you, and the focus is what is different about graph A and graph B, even though both of them are increasing, but shape-wise, we are seeing it completely different. How I can identify that difference. 30 seconds, just starting chat. Go ahead, please. I want to hear more chatting. You want to chat with me? Where is he? Oh, he's coming. See? OK. Can I get a volunteer to see if you had a solid? Yes, please. Louder, please. Yes. No, I don't want to know what it is, because I'm going to teach that. But no, there is something that, based on what we have learned so far, you can describe it. I know there is concavity. That's the hope that we will talk about that. But concavity is just a terminology. There is a concept that we can understand it before the concavity is there. OK, let's see. Yes, please.
The left is decelerating, the right is accelerating.
Let me see if I can get another description there. It's correct, but I just want to see if there's another way. Yes, please.
The rate at which the slope is changing?
I like that one, more mathematical. I just want to have more mathematical way of describing this. Both of them are increasing, but if I look at the tangent lines of different points on this function, as we move to the right, the tangent line goes like this. In other words, tangent line is getting smaller and smaller slope. So slope of tangent line decreases. While unlike that one, in this case, the more we move to the right, our tangent line goes from this to that. In other words, the slope is increasing, becoming more and more. So slope of tangent line increase. The value of the function in both cases are increasing, but in one case, the speed at which this is increasing is decreasing, and the other one, the speed at which the value of the function is increasing is increasing. And that is why we are finding these shapes. This one we are going to call concave down. This one we will call it concave up. Well, to be more precise, this is concave downward. This is concave upward. That is the property of the graph of the function that we want to discuss in details. And I will write the definition first. Obviously, we already have it here. Definition. Let f be a differentiable function on the interval AB. F is concave upward on AB if, remember, slope of tangent line is nothing but f prime. Yes? And what we have described here is that for concave down, the slope or f prime is decreasing. For concave up, slope or f prime is increasing. So here is if f prime is increasing on AB, f is concave downward yes, downward on AB if f prime, not f prime is decreasing. And this property is important for us because it's saying something about the graph. Now we have a bit more properties to identify the graph of function even better. Not just increasing, decreasing, but also how the concavity goes. Well, you should see concavity upward, downward as a property like increasing, decreasing. And then you should ask yourself, okay, what is the right way to find concavity upward, concavity downward intervals of a given function? And that is, well, straightforward result of this definition. Concavity and second derivative. Remember that the sign of the first derivative was about increasing, decreasingness of the function. Now, concavity is about increasing of f prime, and f prime increasing means that f double prime, which is the derivative of f prime, must be positive. So that's what it is trying to say. Let f be differentiable and on AB. Then if f double prime is bigger than equal to 0, f double prime is the derivative of f prime. If a function has positive derivative, it's going to be increasing. In other words, if f double prime is positive, f prime is going to be increasing. And that's how we find concavity upward. If f double prime is 0 on for all x in AB, then f is concave up on AB. If f double prime is negative for all x's in AB, then f is concave down. This is the test for concavity. To be more, it doesn't really matter for me to have to include that equality or not. Let me just to be more precise. I will use strictly bigger than 0, strictly less than 0 for f double prime, and that's the test we have. And the point at which this concavity changes from upward to downward, or from downward to upward, we have a name for that once, and I'm writing that as a definition here. Sorry, I'm putting so many definition and theorem right one after the other one, but this is called inflection point. Let f be continuous at C, and f changes concavity at C. Then the point C and f at C is called inflection point. C, f at C is going to be called inflection point, where the concavity changes. Yes, please.
What if the second derivative is equivalent to 0?
I have no condition here talking about the second derivative. It's going to be related to the second derivative. Yes? But I want just you to see this as, can we find where concavity changes from up to down, from down to up? If the function is twice differentiable, f double prime positiveness goes upward, negativeness goes downward. So if your second derivative, your second derivative is a continuous function, you're going from positive value to negative value. Somewhere there should be 0. That's how it is related to the second derivative. But this definition is a bit more than the second derivative existing. Yeah? Two things I want you to know. Two level of understanding I want you to develop. One, how does it look like concave up, concave down, and then relating it to the f prime being increasing or not. The second thing is this tool here, that Like the first derivative, the second derivative has something to tell about the graph of function. The first derivative was all about increasing, decreasing. The second derivative of function is about concave up, concave down. That's all we are trying to work with today. And we will use this understanding of the concept to create the second derivative test. Let's do some examples. Find concave up-down intervals and inflection points of the given functions. I will have two examples. I'll start with f of x. F of x is x to the power 4 minus 4x to the power 3 minus 18x squared plus 12x minus 3. We are trying to find intervals on which the graph or the function is concave upward or concave downward. And also, I'm interested in finding inflection points. Go ahead, I'll give you 90 seconds. I'm hoping that you will start doing the second derivative. And remember, we are looking for where it is positive, negative. In other words, you're trying to find the sign table for f double prime, the second derivative. Go ahead, 90 seconds starts now. I'm interested in finding second derivative. I start with the first derivative. 4x cubed minus 12x squared minus 36x plus 12. Then the second derivative is 12x minus 12x squared minus 24x minus 36. The second derivative, I want to find where it is positive, where it is negative. So I need to start finding points at which this is 0. But if I factor out 12, factoring this is not difficult. I'm looking for two numbers which add up to -2. When I multiply, I get, that's 3, -3, yes. When I multiply, I get -3. When I add them, I get -2. That would be x minus 3x plus 1. Yeah? And from there, we find the 2 points where the second derivative is 0. Why do we find that? Because that's the starting point of my sign table, x f double prime x, negative infinity, -1, 3 plus infinity. At 0, At these points, we have 0. And then you do whatever methods you know. I get these ones. If I know where it is positive, where it is negative, then that's it. That's what we were looking for. We are just trying to figure out positive negativeness of f double prime, and then this theorem will do the work for us. So if on this interval from negative infinity to negative 1, it's going to be concave upward because f double prime is positive. Are you guys okay with that? That's concave upward. This is concave upward. This is concave downward. What about the inflection points? Inflection points are the points at which concavity changes. In other words, if f double prime is continuous, exists continuous, then it means wherever we go from positive to negative or from negative to positive, in other words, wherever the function, the second derivative, g or f double prime is equal to 0. But remember this notation. When it comes to the inflection point, you should give me a pair of numbers. I want to have a point rather than x value or y value. In other words, inflection points are -1 and f at -1, and 3 and f at 3. Well, -1, I plug into this. This is 1. My plus 4, that's 5. Minus 13, minus 18, that's -13. Minus 12, that's -25. -28 or something like that. The second one, I'm not going to evaluate that one. But when I ask you what is the inflection point, you have to give me those two numbers. I'm not interested in knowing -1, 3, or f at -1. I want to see this and this when you evaluated f at 3. Okay? That's just a notation that we have to follow. Any questions, any comments? Are we all okay with the concept? Yes, please.
Are we allowed to use union when stating the interval?
Sorry, what was it?
Like the union symbol when showing the interval?
Oh, when it comes to the writing the intervals, I would say you write this and this interval. I don't want you to put union there, yeah, because there's conceptually something wrong with union if you put it. Could be wrong. I mean, not always. Could be wrong. Any other questions? Any other comments? By the way, this is not U or union intersection. This is just I'm showing concave upward, concave downward. That's what I am trying to put as the notation. Any other questions? Any other comments? Does that mean we are ready to do another example? Yeah? Well, even if you're not ready, I don't think you have much choice there, but do another example. You're trying to do those two things, concavity upward, downward intervals, and points of inflection or inflection points. Go ahead, please. You get 90 seconds. Is this about that or about that? Can we do after the 90 seconds? Okay, I'll ask you the question after. 90 seconds started now. The inflection point? No, you have to evaluate it. That's difficult for me to. That's yes. So the inflection points you have to evaluate and get two numbers like -1, -28, and the same thing for the other one. So let's start with differentiating this one. Derivative of numerator times the denominator minus numerator itself times the denominator over the denominator squared. And that gives me x squared minus 2x squared. So 1 minus x squared plus 1 to the power 2. G double prime x is derivative of the numerator times the denominator minus the numerator itself times the derivative of the denominator. This is u to the power 2. That would be 2 u prime u to the power 1 less power. And then since I want to work with this, I have to try to simplify as much as I can. What I need you to see here is that x squared plus 1 is a factor on the second term, and x squared plus 1 is a factor on the first one. So I can factor that one out, x squared plus 1. And here I get minus 2x times x squared plus 1. Here we get minus 4x squared, 1 minus x squared. Because there was only one factor of x squared minus 1. And then, now I can cancel that with that. I'm just simplifying g double prime to get simpler function. What is this guy here? This is negative 2x cubed minus 2x minus 4x. Why do I have squared here? This shouldn't be squared. That's just 4x. 2 times 2x is just 4x. And then plus 4x cubed. So then I get 2x cubed minus 6x over x squared plus 1 to the power 3. We cannot do better than that. That's very cool. Now, set it equal to 0. The denominator is always positive. It's not going to make anything bad there. It's not going to be 0. So the only part I have to set equal to 0 is the numerator. And then from there, you get either x is 0 or root 3 or negative root 3. Okay, now negative infinity, negative root 3, 0 root 3 plus infinity. G double prime, and we know G double prime is 0 here, 0 here, 0 here. And then, okay, you have to be careful how to find the signs. But that should be the final good answer for us. And then G itself here, if G double prime is negative, G is going to be concave downward, concave upward. If it is positive, and we have that. And we have 3 points at which concavity is changed. And function is continuous in all the points, including these 3 points. So inflection point are 0, f at 0. Sorry, g at 0. Here is g at 0. So you plug 0 at g, you get 0 over 1, which is, this is one inflection point. The other one is root 3, g at root 3. Numerator is going to be root 3. Denominator is going to be root 3 squared plus 1, which is 4. So, and the other inflection point is negative root 3 and negative root 3 over 4. So you should be able to get these concavity intervals and inflection points right in the spot. Any questions, any comments? Good, yes? Easy. Any questions, any comments back there? If we know concavity, then the second derivative test is easy, just a simple fact of let me show you. So the second derivative test. One thing you should keep in mind is that the first derivative test and second derivative test, both of them are going to tell us which critical points are going to be local max, which one is going to give us local mean. Both of the tests work for determining the type of local max min. Okay, if I have f prime at 1.0, it means that it's a critical point, and assume that f double prime is continuous at C. Now, f prime being equal to 0 means that we are dealing with the critical point. Yes? It could be tangent line is going to be horizontal. Now, if I know that the second derivative is negative, that means that my function should look like this. The only way I can fit a function with concavity downward is like that. And that is a local max, yes? If it is concavity upward, the only way I can sketch around that point is this, which is local min. That's the second derivative test. If f has a local max at C, if f double prime at C is negative, f has a local min at C if f double prime C is positive. There is this last case, which is very important. If f double prime is 0, then our test is not going to give us any meaningful or any result. In other words, if f double prime is 0, then the test is inconclusive. So you have to be very careful. When f double prime is 0, the test didn't work. We cannot say anything. It doesn't mean it's not local max. It doesn't mean it is not local min. Our test is not working in that case. Does this make sense? Yes? I will give you 30 seconds, again, another discussion with your friend. The goal of this discussion is that we already know what is the first derivative test. We know what is second derivative test. I want you to talk to your friend and figure out what is different, practical difference between the first derivative test and second derivative test. I know that we are using the first derivative on the first one, the second derivative on the second one. But practically, there is a big difference between first derivative test and second derivative test. I want you to talk to your friend and identify what is that difference. Go ahead, please. 30 to 40 seconds. Okay. Does anyone want to share their ideas, their discussion with their friend? Any volunteers? One, only one, please. Yes, please. On the first derivative test, I'm trying to say it louder. Go, please.
Test, you use like where the max and min is.
Okay.
Whether it's a max or min. So like, derivative test to figure out if it's like which one is max and which one is min.
Wait, the first derivative test also tells us which one is local max, which one is local min. But the practical way of doing it is a bit different. Yes, please.
Second derivative test tells us inflection points where the first does not.
Let me see if I can find. The second derivative test, I know that there are other things you can attach to the second derivative, but I don't want you to think of second derivative test of all other things. The second derivative test is specifically these three statements, which is about local max and min. But when you're trying to run it for an example, there's a huge difference between the first derivative test, second derivative test. Yes, please.
To do with the concavity.
Well, I mean, the second derivative has something about the concavity, but the test itself, remember, I will take this one as the last one.
You don't have to get like points, you only need to get one.
Exactly. When you're doing this first derivative test, you have to have the full sign table of your first derivative. In other words, you have to know what is happening around that point, which is some work that you need to do and find the whole sign table. But when it comes to the second derivative test, you just need to evaluate your second derivative at that given point. The value of the second derivative only at that given point matters, not other points. It doesn't matter what is happening around the other, that point on the second derivative test. Only that value. For example, if I want to run this one with the first derivative test, obviously I have to always find the critical points, which in this case are 2 points. If I want to run the first derivative test, I have to find the sign table of f prime. But with the second derivative test, the only thing I need to do is plug in the critical points into your second derivative. Here's our second derivative. 2 minus 6 over 8. Minus 4 over 8, which is negative half. The second derivative is negative. The second derivative test says that f has a local max at x equal to 1. G double prime at negative 1 is, if you plug in, you get negative plus, so you get 4 over 8, which is a positive value. Only at that point, you don't need to know more. Then f has a local min at x equal to negative 1. Just be careful. It seems a little bit counterintuitive. When the second derivative is negative, it gives us local max. When it is positive, it gives us local min. Just keep that in mind. Only the value of that function at that point, the second derivative at that point matters. Any questions, any comments? Let's do this example. F is twice differentiable. And someone has told us negative 1, 0, and 2 are critical points of f. And someone has given us the second derivative, sine of x pi over 2 plus 2e to the power x. Find local max. Find which one of these critical points going to give you local max, which one is going to give you local min. Go ahead, I give you only 1 minute. And you obviously need to use the second derivative test. Yes, go ahead, please. $30 seconds, 20 seconds left, not 30. We know critical points, so we just need to plug in to our second derivative. So at negative 1, this is going to be sine of negative pi over 2 plus 2e to the power negative 1. This is negative 1 plus 2 over e. Is this a positive number or negative number? Negative. Who said that? Can you help us figure out better why? Oh, you're setting E to be 2 something. Or maybe do this. Yeah? This is negative 2.7 something something. Plus 2, it's going to be negative 7 something something. So this is negative number. So F has local, it's negative. So local max at x equal to negative 1. How about F double prime at 0? This is going to be 0. That's going to be 2. So this is positive. F has local min at x equal to 0. What happens at 2? Sine of 2 pi over 2 is sine of pi, which is 0, plus 2e to the power 2. It is again positive. So F has local min at x equal to 2 as well. Any questions, any comments? I have one more question. Probably I'll go. Oh, we have 2 minutes. This should be more than. So I have this function which goes like this. We are given the graph of f prime, not f, graph of f prime. Find concavity intervals of what? Of f. Find increasing, decreasing intervals of what? F, and find local max or local min of f. Write it down, maybe 20 seconds. 20 seconds. Think about the first one. What are the concave up, concave down interval for the function f if this is f prime, the graph of f prime? We do this, yes? It's concave up means f prime, f double prime positive, but that is equivalent of saying that f prime is increasing. Because f double prime is the first derivative of f prime. So that means that we have to find where this is increasing. Negative infinity to negative 2. From 0 to plus infinity is concave up. Sorry, I finished soon. And for concave down, you find where it is decreasing, which is from negative 2 to 0. Goes down from that way. Other parts, we did an example last time. I think you have enough content there to do that one yourself. Have a great day. Just keep in mind, tomorrow one of my colleagues is going to cover the class. You have to be nice with them. I will ask them. If you're not, you're in trouble.